comes up frequently in my work, and I'm sure lots of the other consultants at Start Central as well, in that we work with people who want to estimate relative risk, right, and report relative risk. But there always tends to be a bit of a question of, how do you best do this? There's a variety of methods you might come across, and the question that I was kind of interested in here is, well, are these different methods any good, right? Which one should we actually use? Clients that come to me tend to have their own preferences. And to be honest, I often am inclined to kind of, go with what their preference is, unless I think it's terrible for some reason, right? But I do wonder, what should I actually do, right? Am I recommending the best thing here? And so really, this was a little bit of an excuse for me to find out, right? And so we can find out together. So what's this thing here floating on my? I don't want to set up any professional videos. Thank you very much. The context in which this comes up tends to be something where we're interested in the probability of some event occurring, right? And that I work a lot with people in clinical settings, right? So this might be something like or the data might be something like people that died within, n months after the admission to hospital, or that sort of thing. Or maybe we're interested in recovering from injury or disease progression, right? So the number of people that progress to sort of a more severe state of cancer, maybe. And typically, the focus is on identifying risk factors, right? And ideally modifiable risk factors, right? So things that we might influence through interventions or that sort of thing. And there's a variety of studies that do this. Oops. And what we want to do is kind of measure changes in risk, right? That's the thing we're interested in. We want to know if we give people this treatment, does that reduce their risk of a poor outcome? And how much does this risk change, right? We want to quantify the change in risk. And so I'm going to use a data set throughout, well, at least the first half of this talk, to look at this in some slightly more concrete way, right? So we have some real data to kind of dig into and see what different methods do. And so this is a data about heart attack cases. There's a lot of cases, right? And they were collected over some period of time. And the form I have the data in here is that it has been cross-tabulated according to various factors. So there's 3 age groups. There's actually 3 of everything, right? There's 3 age groups. There's 3 times to treatment. And either there's people who get treatment quite quickly, within less than 2 hours, or 2 to 4 hours, or more than 4 hours. There's the severity of the heart attack assessed based on a sort of heart attack severity scale. And there's also 3 different geographical regions. And one question we might ask here is, what is the effect of treatment delays on mortality rates, right? So, I mean, you'd imagine that people who have to wait longer to get treatment will do less well. That sort of makes intuitive sense, but the question is, how bad is it, right? And how much can we improve outcomes potentially by reducing response times, right? So that's what we're going to focus on for the example, right? I'm not going to say much more about, age and severity and geography. I just going to pretend that all we're interested in here is the sort of the comparison between the more than 4 hours and less than 2 hours, right? That's kind of the sort of extreme comparison there. And what we want to do is switch off, is quantify the change in step. So the question is, what's the effect there? And we obviously have two risks here, right? So there's, yes?
What type of study design is this study? Question.
Well, it's a cohort study, I would think, right? So I'm a little bit fuzzy on how exactly the collection here happened, right? So this might be just based on historical hospital records. But the important thing is that everyone who had a heart attack was included in the study, regardless of what their outcome was, right? So there are two different risks we are dealing with here, right? One is the risk of death for the people that got treatment within 2 hours, and the other one is the risk of death for people whose treatment was delayed, basically, right? And okay, this does not work right now. There we go. And now, one way we can look at this is the relative risk, right? That's what we are really talking about here today, mostly. The death risk ratio. But there are other ways you could quantify this difference, right? So you can look at absolute difference in risk, which is also something you may be interested in, but that I won't talk about today. Or you could quantify this with an odds ratio, which you've probably also have come across in the past. And so there, to get the odds ratio, we'd first calculate the odds, the odds of death in each of the groups, and then the odds ratio is the ratio of those two odds, which may seem like a somewhat roundabout way of looking at this risk, right? And odds ratios are kind of nice, and we'll come back to that later on, but they are not very easy to interpret, right? A big advantage of relative risk is that it makes intuitive sense, right? If I tell you the relative risk is 2, then you know that the people in one group are, twice as likely to die than the people in the other group, and that's really easy to understand, and it seems of some practical relevance, right? So, and that is why people that come and talk to me want to use relative risk, because it makes sense to them and it makes sense in the context that they work in. So that's great. And so we're going to look at relative risk, right? It is important, though, to realize that relative risk isn't always an appropriate measure to use. So if you're dealing with case control studies, which are also quite common, where you recruit people into the study based on their outcome, then don't use relative risk. You can't really get a meaningful measure of risk that way. All right. So, but in our case, it's all fine, right? Relative risk is all good. So we can, of course, it's easy to calculate, right? It's just, the ratio of two things that we can look at our data and we can get estimates for the risk in each of those groups. That's easy. And so, I can look at this table and calculate the relative risk, and that's all good. And if I want to, I can also calculate the odds ratio, which is, as you know, similar, but not the same. Now, if the only thing I need is some sort of overall measure of relative risk, that's good, right? I'm done. Time to go home. Thank you very much. But really, typically things are a little bit more complicated, right? And we have covariance we might want to control for, and all of that. And really, what we want is a regression model, right? Regressions are great, and you can do all sorts of interesting things there, but it kind of raises the question, well, which model, right? How do we set up this regression so that we get relative risk estimates out of it that we can work with? So in our example, we kind of want to know about the risk of death for our two groups here, but we want to control for things like age, severity of the heart attack, and the region they came from, right? Because these all are likely to be also important. So we shouldn't just ignore them. And now, how do we do this? The first thought you might have is, well, if I have outcomes like this, where it's a binary outcome, where people either die or they don't. And I know when I have data like this, then I use a logistic regression, right? And logistic regressions are great, but they don't produce estimates of relative risk. They give you odds ratios. And sometimes it happens that people run a logistic regression, they get an odds ratio, and then they say, well, really, this kind of is this thing, and we interpret it as if it was relative risk. But you should not do that, because odds ratios and relative risk are not the same. And so here I have this little graph there, which shows you how the relative risk estimates and the odds ratio estimates you get from the same data differ. And as you can see, if the baseline risk, like which in our case would be the risk in the people that get treatment quickly, is really low, then the two are kind of similar, at least if the risk ratio isn't that large. But fairly quickly, you get larger differences. And that's not great. So, right, odds ratios are not good estimates of relative risk, is what I'm trying to tell you. So if you're after a relative risk, just using the odds ratio, that's not the way to go, right? And so thinking a bit further, so in logistic regression, what we do is we model these of log odds, right? And that then gives us odds ratios as answers. If instead we just model the log of the risk rather than the odds, then we would get risk ratios. And that's what we want, right? So can we do that? Well, yes. We can use a model that's very similar to logistic regression, but instead of using the transformation that gives us log odds, we just use a log transformation. And in amongst statisticians, we call this a binomial GLM with log link. And so that's a thing. That's something. That's a perfectly fine model, and you can have regressions model like this, and then the coefficients will be the log of relative risk, right? And we can look at those and get answers. Life's great. So we can set up this model for our heart attack example, and it's like this. That seems like it's easy enough to do. And you can do this in a few lines of R code or in SPSS. It's not a problem at all, except that my R code kind of gets cut off there, but it's fairly simple stuff until you try to run it. And if you run this on this data, this is what happens. It doesn't work. So R will complain that it couldn't find a valid answer and ask you to supply some starting value, so maybe it can do better. And yeah, SPSS will not suggest that you supply starting values, but it will also fall over. Okay, so in R, I went and supplied some starting values, which is kind of feels not ideal, right? Because now you have to pick some starting values, and you then wonder, well, will the answer depend on the starting values I pick? And it seems like maybe that's not great to begin with. And then it will run, it will produce an answer, but it will also warn you that it stopped at a boundary value, which seems kind of alarming. And yeah, so this is kind of not working, right? I should say it can work, right? So this is a somewhat difficult example, maybe. There are other cases where it can work. It's not like it will never work. Oh, yeah, we have a question.
There's a question in the chat that some people say that log binomial regression is a type of logistic regression. Is this correct?
No. Logistic regression, I see up here, where it says, family binomial log. That's where I tell R to fit a log binomial model. If I wanted it to fit a logistic regression model instead of log, it would say logit. So there is a different link function. Think of it like a transformation involved. So it's not the same thing. Yes.
Can I clarify what the outcome variable R is? Because you said it was risk of death, but if you're using individual level data, you only know the outcome prediction.
Yeah, so here, well, as in this data set, we actually have aggregate data, right? So, and you can see that here, so on the outcome here is the number of deaths as well as the number of patients minus the number of deaths, so the number of survivors, right? So in a binomial sort of context, we would think about these as successes and failures. If you have individual level data, you can provide that too, then they're just zeros and ones, right? And in this case, you just have one trial per person, basically. It will still end up aggregating within sort of the groups that are defined by the right-hand side of that model. Okay, so this seems like, at least in this example, it's not working. And that's a bit of a problem, right? We kind of want our things to work and not just fall over. So what we're going to do? So the problem here, so maybe to elaborate a little bit, is that we are estimating a risk here, right? It should be between 0 and 1. That means that there are some constraints that need to apply to our predictors so that we actually get predictions that are between 0 and 1. And there is, by itself, without us doing anything, there's nothing that forces the right-hand side of this equation there to do that. And so it is possible to end up with situations where we either, where we would end up with probabilities that are larger than 1, which is, clearly nonsense, or the thing happens that, happened when I tried to do this in R, and you end up on the boundary, so you end up with a probability that's 1, something like that. So, and then you don't know, is this a valid answer? I mean, it could be answers on the boundary are valid, but that's also where you tend to end up when things go wrong. So, so that's a problem. And the problem is that the general purpose methods that we use to fit these models don't really deal with these constraints very well. So what do? Well, really, there's 2 options we have. I think one is we could use a different method to fit this model, a method that handles those constraints better and gives us reliable answers. Or we could use a different model, right? Oops. So let's look at using a better model fitting algorithm first. Now in R, this does not work in SPSS, I'm afraid. In R, you could use the log-bin package, which provides an alternative way to fit log binomial models, and deals with the constraints. It's just as easy to do, more or less. You load a package and then you fit the same model as before. And it will give you an answer without too many complaints, well, without any complaints, really. It will estimate the relative risk. And in this case, the answer is 1.1 something. And you get a confidence interval for that, and all of that is fine. It can be a bit slow. So in this case here, because I'm actually running this as part of compiling the slides, I did not want to wait for several seconds just for this every time. So I set it to start with the coefficients from the log binomial model I fit before, and that goes really fast. But without that, it actually takes I think almost a minute to get there. So that's a lot slower than you might like, especially if you're like me and do lots of simulations for this talk and have to fit this like a thousand times. It can still produce solutions on the boundary, I think, so which you might find disconcerting, but it's it does, as far as I can tell, a lot better than just the the plain GLM I'll show you. But there are other options, and we should consider those too. One thing that's quite popular with a lot of people that I work with is modified Poisson regression. So what's that? Well, so basically the idea is we don't have to worry about constraints if we don't have too many constraints. And we do want a model that estimates rates, right? That's kind of what we are all about here. And Poisson regression kind of does this. So maybe that's a good place to start. I mean, you might wonder, how is Poisson regression the thing to use here? Because if you know anything about Poisson regression, then you know that's a model that you use for count data, right? And we aren't really dealing with counts here. We're interested in rates. So what's going on? The general idea, how you might set this up is that we are kind of trying to estimate a rate like sort of like this one, and it does not work. That's great. Well, like this one anyway. Like this one. And that's not a count, right? But and again, everything's happening on the log scale as before. But we can be kind of clever and rewrite this model, right? And so what happens is that the log of that ratio, that's the same as the difference of the logs, which is the second line there. And then we can just take the sort of our exposure here, the number of, in this case, the number of patients, and add that to both sides. And now we have on the left-hand side the number of deaths, which is a count, right? And on the right-hand side, we have this extra term, which is just the log of our exposure, basically. And that's called an offset. It's not an extra predictor in your model. It's just a sort of a fixed term you have there. And that's fine. It can still result in risk estimates that are larger than one. So we didn't get rid of that problem entirely. But so in practice, it seems to be a lot less prone to do that than the log binomial model is to run into trouble. Oops, getting too fast. Yeah, and my main complaint about this model is it's just the wrong model, right? And we know it's the wrong model because we are not dealing with Poisson data here at all. Now, that doesn't mean that it will give us the wrong estimate necessarily, but it does mean that the standard errors it will produce will be wrong, and we know they will be wrong, so we can't use it. So instead, we use robust standard errors, so the standard errors that are robust towards misspecification of the model. And again, you can do this in R, you can do this in SPSS. In SPSS, if you do it through the menus, I'm showing you the syntax here because I did not want to take like 5 different screenshots to show you how to navigate. And if you want, you can take a copy of this syntax basically and start getting there. But in the menus, there's just a box that you tick to say robust standard errors. And in R, you can use one of the ways you can do is you can use the sandwich package to get allow you to get sandwich estimates. That's what this type of robust standard error is called. And so I can run this, and it will work, no trouble at all. And it will give me estimates and confidence intervals. Fine, right? So it does seem to work. The estimate I get is quite similar to the one I got from logbin. And the confidence interval seems to be a bit larger. All right, but it's the wrong model, right? So, but that's just me, I guess. Okay, so, but what if we did use logistic regression? I mean, we know logistic regression works for this type of data, right? It's a sort of tried and true model. It doesn't have the issues with constraints. In most cases, it just works, right? So that seems attractive, but it gives us odds ratios. And we don't want odds ratios, we want relative risk, right? Because relative risk we can understand. Well, so we could convert them, right? We could take the odds ratios and convert them into relative risk. That's a thing you can do, provided that you know what the baseline risk is, right? And of course, in practice, you usually don't know, right? We don't know what the true baseline risk is. But we do have an estimate for the baseline risk that we just get as part of fitting the model, basically. So we can do this. We can fit this logistic regression, and so you see now here the link function is logit, not log. It's not the same thing, although it's kind of similar, I guess, but it's not the same thing. And we can get an estimate of the baseline risk, and we can convert all of this into relative risk estimates, and we get an estimate, and we convert the bounds of the confidence interval, and we get those. Again, everything quite similar. And you can do this in SPSS, right? You get the logistic regression and you get the estimates you can convert. It's fine. There's a problem here that I did not point out. What's the problem? Exactly. You estimated the baseline risk and you're not accounting for the uncertainty in that estimate, right? So, I mean, it doesn't really look like here, but I'm willing to bet that this confidence interval is too small. So that's a bit of a problem. We could go another way. So if you're an R, the EM means package can do a similar sort of conversion for you. And it can basically, EM means can convert between all sorts of transformations, right? And so you can fit a logistic regression model, which gives you, logit scale estimates, and then you tell EM means, well, I would like you to turn these into log scale estimates, and you'll get relative risk. And so if you're interested in the R code, here's some example where you use regrid here to do that transformation, basically. And that will then give us yet another estimate of the relative risk with a confidence interval. And so this also works. Yes?
And does that take into account the standard error of the?
Good question.
Yeah, sorry.
Can you repeat?
Oh, I see. Yes. So the question was, does this take the standard error into account? I will admit I'm not 100% sure what it does internally, but I think, well, and I think that this conversion isn't necessarily guaranteed to be perfect, right? I think the chances of it at least capturing some of the uncertainty is better than if you just ignore it, right? So if I had to choose, I would go for this rather than the straight up conversion. But yeah, it's a good question. How good a job does this actually? And really, that's my next point, right? So, well, we can do this. All of these things, all of these approaches, they give us estimates. They give us confidence intervals. They all look kind of similar. So which one should you use, right? So far, I haven't really answered my question because, well, these all kind of seem samey. So, which one is it? yeah, it's kind of hard to tell just looking at this data, right? And at each individual example you look at, it's kind of hard to know is one better than the other because you don't know what to choose. So really what we should do is we should simulate some data where we know what the answer is, and then we can look at how well these methods do at recovering that answer. So I went and simulated 9 different data sets for different combinations of relative risk and baseline rate, right? Because both of those might matter in how well different methods do. And this is what happened. So we jump straight to the summary. The baseline rate is going across columns, right? And different relative risk is going down the rows. And you can see that when the baseline risk is low, everything is kind of the same, right? And I mean, they all seem to do a decent job, basically. The confidence intervals are quite wide here because at this low of a risk, there are just very few cases in the data. I mean, I simulated, I think, 1,000 observations in each group, so that's quite a large sample. But if there's only a 1% baseline risk, that's still only 10 people, right? Then as the baseline risk and the risk ratio increase, things start to kind of go off the tracks a little bit, right? And you note that down here, let me try this again. No, really not. All right. Down here, the just the GLM failed completely, right? So it did not produce any results. I did not try to give it, starting values or whatever, because too much hassle, but it just failed. But everything else is also kind of off, right? For the kind of less extreme examples, things seem to work fine, and they mostly seem to do similarly well, right? And so based on this, it seems like it doesn't matter that much which one you use. Maybe don't use the straight GLM because it might fail, but the other ones are kind of doing fine, except in extreme cases where maybe they don't, right? Now, I should say that this, like a relative risk of 3 with a baseline risk of 0.3, is really extreme, right? The risk in the other group here is 0.9. Right, so it's a big difference. I also, looking at this, kind of feel suspicious about these confidence intervals with the high baseline risk. They seem really small. And a lot of them end up not including the real value, which can happen. It should happen in about 5% of cases, right? But it happens in the one example we look at, so that's a bit suspicious. Well, only one thing for it, we got to investigate more, right? So I simulated some more. So now what I did here is that I repeated the simulation, right? And generated new data from the same settings. And then each time I did this like 1,000 times for each of the 9 data sets. And then I counted how often each method produced confidence intervals that included the true value. And this is what happened. So here, each dot is of the confidence interval coverage, right? The proportion of confidence intervals that did include a true value. It should be 95%, right? Because these are 95% confidence intervals. In the sort of more benign settings, that's mostly what I got. I mean, they vary a little bit. Sometimes they're a little bit large, sometimes they're a little bit small, but they kind of vary around 95%. When the baseline risk increases, something breaks. And in this example down here, it's just completely broken. One thing, I mean, again, everything sort of behaves the same, right? What kind of stood out to me is that the sort of straight up conversion of the odds ratio definitely does worse when things start to get difficult. And it's sort of, you know, it's just not right. The confidence intervals are too small, right? Even more so than other methods might be. So our suspicion there that you're not accounting for that uncertainty really that was justified, I think. So yeah, so this worked pretty well for situations where the baseline risk was, you know, kind of small to moderate. And or when the sort of relative difference between the risks wasn't too large. But yeah, in more extreme cases, neither of these methods does seem to do that well. I don't quite know why that really is, but I suspect it is that you're starting to run afoul of that upper boundary. And things then don't work out so great. So should we maybe just use automations? Is my question to you. This relative risk, it does seem to be a lot of trouble, right? And now, as part of doing all these simulations, I was also fitting logistic regression models, right? Because I was converting odds ratios to relative risk. So what does the confidence interval coverage for the odds ratios look like? Well, it looks like this. And now the odds ratios aren't as nice. The numbers aren't as nice because some of the combinations of baseline risk and, you know, treatment risk, or whatever you want to call it in this made-up example, it don't make for nice round numbers, right? They make for nice round odds ratios. They make for nice round relative risks. But you'll notice the scale on these plots is different, right? They don't start at 0. They start at like 0.93 or something. So these are really close to 0.95, where they should be. So our standard errors for the odds ratios, they are perfectly fine, right? It's just that when we took them and tried to convert them to relative risk, that something went wrong, and everything fell over, and you know, we ended up with confidence intervals that were way too small. So here's what I think you should do. Use logistic regression to fit your model. And use the odds ratios you get from that for your inference, right? If you want to know whether there's a significant difference or, you know, a significant reduction in risk from your intervention or whatever it is you're doing, look at the odds ratios to make that decision. But you still will struggle to interpret those odds ratios, right? And whatever you do, don't interpret them as relative risk. But what you can do is you can say, well, this is the odds ratio, and you know, here's my estimate of the baseline risk that I just produced. And you can use that to convert the odds ratio into a relative risk. And you can use that to communicate what the change in risk is, right? I mean, you could convert to absolute risk difference as well, if you want to, right? Both of those are possible, and whichever one makes more sense for you in communicating the thing you're trying to do, you should do. I think that's perfectly fine. I mean, the conversion works, right? But the estimates you get from that are fine. I mean, they're close to what they should be in most cases. So that's okay. Just don't do inference on the relative risk, because that clearly looks like it might turn around and bite you if you're a bit unlucky and are in a situation that's a bit more difficult. Yeah, so that brings me to the end of this seminar, and we might have some time for questions. And also, this is the last seminar for the year, so we hope to see you all again next year. Yeah, but I take questions. Yeah, Nick.
Oh, Rachel, Peter. So just to summarize, tell me if this is right or wrong. So when you go from logistic regression into EM-means, you go onto the absolute probability scale, then the point estimate of the you can get the point estimate of the relative risk by dividing the estimated risk by the other one. Is that okay? Is that point estimate okay? I mean, obviously you don't get confidence because of standard error. But is that accurate? And then the absolute risk difference, we could just do a contrast on those probabilities pretty simply. So that those two would be.
Yes, I mean, you could, I mean, it means, oh, sorry, well, that's a long question to summarize. So the question was about how to get the relative risk and absolute risk difference estimates from EM-means. Is that?
Yeah, that's right. Yeah.
So well, one thing you can do is you can do this regridding thing in EM-means, right? Which is what I did here. Somewhere this is the code, and so that will just give you relative risk estimates for for your different groups that you define in EM-means, right? But you can also get so the probability scale estimates for each group, I think, and then if you look at a contrast, that will give you the difference, and that should give you confidence intervals too, I think.
Even dividing the two probabilities, can you divide? I don't think you can divide.
No, you want to get EM-means to do it for you.
Okay.
I think so. I haven't looked at doing this for the difference, but I think you should be able to get it to do that. Yes.
Thank you. That was really helpful. I'm an epidemiologist, so it's kind of bread and butter for us. Well, the idea of using relative risks and odds ratios is bread and butter for us. But so most epidemiologists don't actually know that you can generate relative risks in binary data, and I've done it myself as part of my PhD in a survey situation, and it's, I think I'm worried that I wouldn't be able to get published if I use these alternative methods, I guess.
Yeah.
Because it's very unfamiliar in the public health space. But it's very helpful, I guess. Sorry, this is more of a comment, but it's really helpful to know that maybe we don't use that sandwich estimate, that maybe the estimates I got when I applied that to the survey data, the confidence intervals might have been wrong.
Yeah, well, so the estimates will be fine.
Yeah.
But yeah, the standard errors will be wrong to varying degrees, I guess, depending on where in the space you are. But the point about publication, that's very valid. And I think as stats consultants, we need to be quite mindful about this of your common practice in different fields. And that if we give advice on, you should do this because that's best practice, it might get rejected in the field because nobody does it. And so that's definitely something to be mindful of. I think definitely my recommendation would be to present results in terms of relative risk, right? But that doesn't necessarily mean that you can't do your analysis on the odds ratios anyway.
Well, that's what I do. I'm guilty of doing that. And I just express it in terms of odds, but I can't interpret odds ratio.
Yeah, no.
I don't know what they mean. The risk is a probability measure. The relative risk is the ratio of two probabilities. And you can just say that the risk is X times higher. Or lower.
Yeah, absolutely.
It's just so much more
Yes,
intuitive.
I completely agree.
Yeah.
And I think they're a great tool for communication, right? And to understand, right? To communicate to others, but also to understand yourself. And in no way would I suggest that you should stop doing that. I'm just saying that it might not be, basing some inference on that might be problematic. And so maybe we shouldn't do that. But I think the two can kind of live side by side. I mean, it's just two different ways of looking at the same data, right?
So you say odds ratio with confidence interval and relative risk without confidence interval.
Maybe.
Right?
And I mean, in terms of kind of understanding what this data is trying to tell you, right, and communicating that to others, you mostly talk about the point estimates anyway, right? And so it's important to kind of be aware that there's uncertainty, and whether or not this relative risk or the difference in risk you observe between two groups, say, is actually large enough to be excited about. But that decision maybe you should make on the odds ratios. But then once you get excited, then you can look at, what does this mean in terms of, how the risk changes. And that's something we can talk about, and that we can then make decisions about, whether we should, change the way we do things to, improve outcomes or, that sort of thing. Oh, yes.
What values of the odds ratio or range of odds ratio produce accurate or nearly accurate conversion to relative risk?
Well, so if we look at this handy plot here, right? So the question was about when are odds ratios and relative risk similar, basically. The smaller the baseline risk is, the less of a difference you get for a given relative risk. And the smaller or the closer the relative risk is to 1, the less of a difference you get for a given baseline rate, right? But they're only ever the same at 1, right? So if the relative risk is 1, the odds ratio will be 1 as well. But if they are not 1, the odds ratio will always be further away from 1 than the relative risk. And I'm very much opposed to the idea that, this is close enough, we can just interpret the odds ratio as a relative risk. Just don't do that. Were there more questions?
Yes. Have you looked at the R packages like FER, PHE, and if so, are they useful?
I haven't. So the question was about specific R packages and whether I've looked at them. But I have not, unfortunately, so I can't comment in detail. Yeah.
What do you think about the idea, Peter, of always reporting, say, an additive scale as well as multiplicative. So if you're going to do relative risk, also put in the absolute risk difference. So people can think about them in both ways and, you know, choose the other. Just as a standard for everything else.
Yeah, so, well, I don't know about mandating it to, you know, so the question was, should you always report relative risk as well as absolute difference? And I mean, those are two different ways of looking at the difference in risk, right? And I think they're both useful. And the relative risk might obscure the sort of absolute difference, and the absolute difference might be not what you think it is, just looking at the relative risk, right? So for example, when the baseline risk is quite small, then it's easy to get a large relative risk that might correspond to, you know, tiny change in actual risk that you might not actually feel you should worry about. So it's definitely useful to report them, I think. And there's no harm in providing more information, right? So I'm all for it. But also different measures of change in risk might be more meaningful in, you know, certain settings.
And then it's when you report the relative risk, I think you always have to report for the baseline because what. So
Yeah, so
you need to report both the relative risk and the baseline so you know what you're talking about. Whereas the absolute difference, it's easier to see what's happening, right?
yeah.
And also, like, one final, what about log relative risk? Because, you know, it's a ratio. So, you know, to compare relative risks with each other, if you do that numeric analysis, you take the log.
Yeah, well, so that's the other thing with relative risk is I don't think it's useful in meta-analysis because it depends so much on the baseline risk that you can't just include the relative risk in a meta-analysis and hope to get some meaningful output. Because these studies you include might have dealt with populations where the baseline risk is different. And then you can't compare the relative risk for different baseline rates, right? Which is another reason that maybe you should always report odds ratios, because those you can use in a meta-analysis. And so by reporting the odds ratios, even if you don't do anything else with them, because you just focus on interpreting things in terms of relative or absolute risk, you make them available to future studies so that they can do meta-analysis. Right. Yes.
Just like to comment, it'd be really nice if you wrote that up, all this up as a paper.
And also because I've been seeing lately that people want the modified Poisson, whatever, right? And
Yeah.
this will help just to show, see, you shouldn't be using it either.
Yeah, that would be, well, maybe if I find the time. In the meantime, the recording will be on YouTube, so so you can point people, you know, that you maybe want to steer away from modified Poisson to this at least.
Yeah, that's easier because I put in some papers, but this one, I guess, is going to be very useful.
Okay.